Hello, everyone. Thanks for staying until these late hours of today and the last day of the meeting. So this talk is really about how telcos can use a component that we introduced in Neutron to create flexible interconnections, in particular relevant in the context of NFV, based on the BGP VPN protocol. So I'll first introduce what BGP VPNs are. Explain that they are a key building block for telcos. Usually this technology is not known by everyone, so I'll do a short one-slide reminder on this protocol stack. I'll also explain why we like to use dynamic routing in this context, which is not something we necessarily use with BGP VPN, but something which goes along pretty well with BGP VPNs. To make this practical, I'll give an example based on the VPC, which is one typical NFV use case. And then I'll jump into the core of the presentation, which is really about how we do this with OpenStack, with or without SDN controllers, and what we can do with this API that we introduced in Neutron for BGP VPNs. And to make this even more practical, we'll do a demo, a live demo, so maybe we'll have a surprise. I hope not, but or only good surprises, perhaps. So telcos have a background of using lots of specific technologies. There is the one topic of today, which we call BGP VPNs. Why they are a base building block in the NFV toolbox? It's because telcos require network isolation. We require network isolation because multiple networks that we use for mobile backhaul, for wholesale and business-to-business offers, for tribal play, all these services and networks are not connected to the internet, do not run directly over the internet. So we need to isolate them. And BGP VPNs is a technology that's been around for a while, and that's typically very well suited for this to address this need for isolation. So now, today, or it's been the case for a few years, NFV comes into the picture, and we need to make these work, BGP VPNs, to make them work with OpenStack. So I need to explain you what it is first, just in case you haven't been exposed to the specific technology before. So the base technical principles behind BGP VPNs, simplified a bit, but you will get the key ideas. In the data plane, the idea is to isolate the different routing domains, isolation scopes, using technology that's called MPLS. That's been around for 20 years now, to isolate the traffic on the wire. In this context, MPLS is just an encapsulation carrying packets of a VPN with an identifier that appears in the packet, which is used for isolation. MPLS, if you want to dig into it, is much more than this. But in the context of BGP VPNs, we can accept this simplification to understand what it does. So that's for the data plane. On the control plane, we use the BGP routing protocol. In fact, an extension of the BGP routing protocol that's been introduced in the late 90s, late 90s. BGP basically allows a router to say to another router how to reach a destination. In this case, since we are in BGP VPNs, the routes that we will have in the BGP protocol will typically say, well, hey, this prefix 10.11.00/16 in VPN foo, so we have a particular way of naming VPNs, is reachable via router X using a given MPLS label N. So this is the information that you will find in BGP routes. The VPN identifiers, we call them route targets. They are structured identifiers with an internet AS number and a numerical ID following it. You have also other ways to format route targets. So it's a simplification to call them identifiers because, in fact, you can do much more. You can have complex topology that you build mixing different import and export root targets, but we won't get into this today. You can accept the simplification that it's a VPN identifier. So initially, these BGP VPNs were only for IP VPNs, IP connectivity. This was introduced at the end of the 20th century. Later, the same architecture was extended to allow to do layer 2 connectivity, Ethernet connectivity. In particular, EVPN was introduced a few years ago and is today a technology that's incrementally used in data centers and overlays. The data plane itself was also extended to support other encapsulations, namely MPLS over GRE, MPLS over UDP, and in the specific case of EVPN, VXLAN. So it's an introduction. If you want to know more about BGP VPNs, you will have to do a bit of homework. There are plenty of material on the internet. It's a technology that you need to study a bit to understand very well, but hopefully this will be sufficient for you to appreciate the rest of the presentation. So as I said, something that we want to do very often is to combine BGP VPNs and dynamic routing. And dynamic routing allows us to do interesting things. One of them is Anycast-based load balancing. So as you may know, Anycast is when multiple hosts, for instance, multiple VMs, share a given IP. So when this is the case, you have the opportunity to use equal cost multipass, which is the kind of load balancing that IP and MPLS routers can do. This is really packet-based load balancing with a twist. These devices most often, actually nearly always, use a 5-tuple hash to guarantee that a given TCP session or UDP connection will be load balanced on a given pass without changing to avoid reordering, which typically hurts TCP performance. So it's really packet-based load balancing that routers can do. So if you combine Anycast with load balancing, you can do interesting scale-up, scale-down. A given service IP can be advertised from multiple points, and the traffic to this destination will follow the events where you add or remove a VM serving for a given service. So that's Anycast load balancing. Then there's another reason why we like dynamic routing. The reason is that in many contexts, we need to interconnect our OpenStack platforms to some WAN network. And we have typical drawbacks when we have to interact with the configuration of routers, what we call provisioning. What we need to do in this case is that we need to configure different things on a router, VRFs, which are the VPN configurations, VLANs, static routes. But very often, the router configuration is not managed by the same ops team as the cloud or as the VNFs. And even when it is, it's different tools that you need to introduce to do router automation. The state of the technology today is such that we can't assume that it will be easy to do this configuration in a standardized way. So you will end up with a configuration that's tied to a specific constructs, or sometimes even to a specific CLI of a given vendor. So even when you can do this, you will still need to interconnect to build different tools together to achieve this. So it's hard, and if we can avoid it, then it's a win. And typically, using dynamic routing allows us to avoid at least a large part of this configuration. How? We do it by having the SDN controller advertise BGP VPN routes. In which case, it will be sufficient to have one-shot configuration on the router without having per VPN or per VM configuration. So when a new VM is introduced, for instance, dynamic routing is sufficient to let the gateway, the router, be aware of this new destination without having to interact with the router configuration. So dynamic routing instead of hard to automate router configuration. So these are two things that are useful to do. and particularly relevant when in the context where the routing we want to do is isolated routing, BGP VPN routing. So let's take an example. This is a severely simplified example of a VPC. It's a subset of the different things that you find in a VPC, only P gateways. Don't use this to design your VPC deployment, please. I'm not an expert in VPC, by the way. So this is a simple example where we will have a few P gateways. So P gateways, it's a function that receives the traffic from the end users, from your smartphone, via tunneling that's done through the mobile backhaul in a protocol called GTP. So the P gateway will decapsulate GTP, take your traffic, and give it to the other boxes that will process your traffic before it's sent to the internet. So in this case, what I'm showing is a P gateway which have the same IP address, 3.3.3.3. So it's Anycast. When the components in the mobile backhaul send the user traffic to a P gateway, they send it to 3.3.3.3, and it's routing that takes care of load balancing the traffic to this destination. But for this to be possible, we need to actually, I need to explain the reverse path as well. In the other direction, the internet or the provider backbone that's the intermediate to the internet need to be aware of how to reach a given user. For instance, here the user is 20.0.0.42, and we need to have a way to advertise that this IP, actually the prefix inside which this IP is reachable via P gateways. So if we use dynamic routing with Anycast, we will have the SDN controller advertise that a given prefix is reachable via these 3 ports, which are VM ports. So it will say that this prefix is reachable via a given compute node with a given MPLS label that will result in the traffic being forwarded to the VM port. And if we take the Anycast address of the P gateway on the other side, you will have the address of the P gateway advertised in the VPN that's the connection to the mobile backhaul. And once these advertisements, these BGP routes are advertised, everything is in place so that traffic can flow from end users to the internet and vice versa. And the traffic will actually be load balanced by the IP MPLS gateway. And all this is possible without having to tweak the IP MPLS gateway configuration for each P gateway VM that you will add. So this is a solution that's pretty typical in our space. So now the interesting question is, how to do this in OpenStack? Why we want to do this in OpenStack or via OpenStack networking, the OpenStack networking API. So the initial context, that was actually the situation already 3-4 years ago, is that there are some SDN controllers that support BGP VPN routing, even SDN controllers for which the key architecture is based on actually BGP VPNs, such as Tungsten Fabric, Open Contrail, or Nuage Networks. But there are actually 2 key drawbacks with this. The first one is that each of these SDN controllers has their own API to use or to configure BGP VPNs, or the BGP VPN properties of virtual networks. And second, we lack the possibility to let tenants manage the VPN connectivity. Basically, if you want to allow a tenant to change the VPN identifier, it means that the tenant could actually send traffic into the virtual networks of his neighbor tenant. So we needed an API being SDN controller agnostic and multi-tenant. So an API in Neutron to control BGP VPN features of the various, the set of SDN controllers supporting BGP VPN features. So that's one key part, API related. The second part that was relevant to achieve was, beyond controlling features that are present in SDN controllers, was to have also an implementation in Neutron. And this was important for two reasons. One is that to develop an API and the corresponding Tempest scenario suite and so on, we need a reference driver in OpenStack in the community. And the second reason is that, having an SDN controller is sometimes what you want, but it's also interesting to have, as an alternative, the possibility of having these features in a context where, you want something lighter than a heavy SDN controller. So we end up with a project in OpenStack that exposes an API to control BGP VPN features of SDN controllers and also of a reference implementation. So now we have to perhaps a transition. So these motivations were the root of the project. And 3 years ago, in Vancouver, the project was started reusing components that had been prepared. Not only these components, but using in particular a few components that had been made open source a bit before by Orange. So if we look at the state of networking BGP VPN today, sorry, my transition is bogus. I need to state a few facts. So practically speaking, today, we have a project called Networking BGP VPN, which is one project among the different projects in the Neutron Stadium. So in this project, we cover different features. We have the possibility of defining different types of BGP VPNs. One type is layer 2 to do EVPN, Ethernet VPNs. One is layer 3 to do IP VPNs. We have API constructs allowing us to choose with which granularity we create connectivity with BGP VPNs. We can do that at the network level, at the router level, or at the port level. We introduced in Queens features to allow fine-grained control of routing. We have the possibility of saying that static prefixes are reachable via a VM port. This is something that's also called sometimes a static route, although the name is not perfect because, since you can modify them via the API, it's not really static. But that's the usual lingo inherited from routing culture, I would say. You have the possibility of saying that the routes of a given VPN are reachable via a port. This is a form, that's something that's also called route leaking, and that allows you to do a form of simple but sometimes very efficient and useful service chaining. And we have the possibility of controlling the BGP local preference, which is a property of BGP route, which allows to control how destinations are chosen when you have multiple destinations for a given, multiple possibilities for a given destination. So these were API features. We have drivers for the solutions that I mentioned earlier. So we have drivers for Neutron ML2, for OVS and Linux Bridge. We have drivers for Open Daylight. We have drivers for Tungsten Fabric Contrail. And we have a driver for Nuage networks. So it's a pretty, I would say, exhaustive coverage of the different solutions that allows you to do BGP VPNs today. And also, it's not exactly features of the project. I mean, as end users can see features. It's like complementary features. We have hit bindings, which is very useful. We have a Horizon GUI, which is nice, in particular for demos, although the demo today will be CLI only. And we have a Tempest suite, which is useful because you can apply this suite to any deployment where the service plugin is introduced. So when you use the BGP VPN API, well, you have a very typical workflow here. You have to keep in mind that these BGP VPNs are not like your IPsec VPN for corporate use or personal use, or OpenSSL VPN. It's a VPN for which the operator, the infrastructure, is in charge of isolating the different isolation scopes, address spaces, and it's the admin that's in charge of choosing VPN identifiers so that people don't see the traffic of each other. So your tenant cannot just choose his VPN identifier. You have to have only the admin able to do this. So the first step when you use the BGP VPN API is to have the admin create a BGP VPN object. This is the object where the VPN identifier is stored. And then it will give this object to a project. But the project, of course, will not have the possibility of changing the VPN identifier. The VPN identifier will be a read-only property for tenants. So here, the OpenStack admin has created a VPN. That's an API construct corresponding to a BGP VPN that's in the WAN, or perhaps between two data centers for a tenant project Lambda. And then any user, well, you have different ways of controlling roles and authorization, but a user in Project Lambda can say that, well, his Neutron network will have connectivity to this BGP VPN, and it will do this by creating a different object, which is called a network association, that will tie the existing Neutron network construct with this BGP VPN object. So this is an example for when you want to create connectivity at the network level, but you have corresponding the exact same framework when you want to do connectivity at the router level or at the port level. And sometimes these association objects have additional properties allowing you to control with a finer grain the routing that will be done by BGP, but we won't cover this today. So this is the API. And as soon as it's done, traffic can flow between the Neutron network and the external BGP VPN. So this was the API. We can describe quickly how it's practically done in the OpenStack or SDN components. So first, you will have API calls on the Neutron API, on the BGP VPN extension of the Neutron API. This call will be handled by the BGP VPN service plugin. The service plugin has a typical driver architecture. The operator of Neutron will have chosen a driver that will be the right driver for the backend that is used behind Neutron. So the backend, what I call the backend here, can be Neutron OVS, Open Daylight, Open Contrail, Nuage, or Neutron Linux Bridge. So the actual details on how the driver will communicate with the backend depends on the backend, but the information is pushed to the backend, and then the backend will do its stuff. Again, depending on the backend, the details vary a lot. But in the end, BGP VPN routes will be exchanged with the routers at the border between the data center and the WAN. And based on these VPN routes exchange and the local configuration, the data plane will be configured. So the data plane will typically be the virtual switch of the compute node, but you can completely envision a case where the traffic would be handled by a top-of-rack switch. This was actually a proposal exposed in a presentation yesterday done by Yanwas, Harish, and I don't remember all the names, but they are referred to in the last slide of my presentation. So in the end, the traffic will flow between the VMs and the WAN via MPLS. When we say MPLS, it's MPLS. Different variants of MPLS can be used depending on what you want to achieve. The typical thing that interrupts today easily is MPLS over GRE. That's what IP MPLS router supports have been supporting for a long time, but it can also be MPLS over UDP, which is even better for efficiently load balancing the traffic in the underlay and in between NICs and CPUs. And it can be VXLAN for the specific case of eVPN. So let's do a demo, or I hope we will do a demo. So what we will do, it's not a complex demo, but it demos something pretty powerful, I think. So it's not a demo of, it's not a VPC demo. I mean, today IP gateways are a tiny bit too heavy to run on my laptop. So it's a simple demo where the function that we deploy as Anycast is not a P gateway, but it's a DNS server. So we will have an end user in a given VPN, which we call VPN red, trying to reach a DNS server via the IP 10.8.8.8, which is actually present. This DNS service is present on multiple VMs. And we will actually scale up and down the different VMs that serve the service. And we will use the BGP VPN API so that the reachability, the Anycast load-balanced reachability between the end user and the DNS servers is created thanks to the BGP VPN API. So all this, again, is done without touching the router configuration. There is a one-shot router configuration that's related to connecting the end user into these VPNs, but that's not part of the OpenStack cloud. But the creation of additional DNS VMs does not involve any interaction with the router. And making them reachable does not involve any interaction with the router. So under the hood here for this demo, we have an IP MPLS router running in a VM. We have a simulated end user, which is just a basic VM connected in the VPN. And for OpenStack, we are using a DevStack VM, using the Neutron OVS reference drivers for BGP VPN, using a component named Backpipe, which is also developed inside OpenStack. I added the precision that it's using a recent enough Open vSwitch 2.8, at least 2.8. In fact, I run 2.9 here. Which is a release in which the support for MPLS over GRE was introduced. So we will use MPLS over GRE to carry the traffic between the virtual switch on the DevStack compute node and the IP MPLS router. So in the OpenStack tenant, what we have is a BGP VPN, corresponding for which the VPN identifier matches the VPN configured on the IP MPLS router. This was created before the demo by the admin. We will have simple DNS server VMs. Here there's a twist, there's a trick, so that the demo, so that we can see that we have load balancing. The DNS are configured to give a different answer to the DNS query made by the client. That's not the typical way of configuring a DNS server. That's just for the sake of making it nice to show that the traffic is load balanced. And each VM port will be associated with a BGP VPN with a route set to the DNS server's Anycast IP. So let's do this. OK. So initially, on the top left, on the bottom left corner, we have our end user. So let's try a DNS query. It's not working. We can see on the router routing table that indeed we don't have any route to 10.8.8.8. We don't have any traffic on the virtual switch either. This is on the bottom right corner. We have a TCP dump looking at all the MPLS traffic, MPLS over GRE traffic. So let's start. So this is using the OpenStack CLI. You may have the impression that I'm typing fast, but it's a neat replay tool. I'm not actually typing. So we can see as a tenant that we have a BGP VPN available. So let's start to create a port for our first VM. So it's using just the default private network for this tenant. So we'll create our first VM, DNS VM1 on port 1. And we will have a simple cloud init script so that we start a DNS server. The rest is like boilerplate, not interesting. I will show you the cloud init file. It's actually a simple script that adds our destination address for the DNS service to the loopback. And then it just configures the DNS server to reply 1111 for the Vancouver.demo host. And it starts the DNS server. It's a very simple DNS server present in the Cirrus image. Then we need to say to Neutron that this port is allowed to send traffic with the IP address 10.8.8.8, because by default, Neutron would not let this VM send traffic with an address that's distinct from the address allocated by Neutron itself. And then we will create the actual, this is really the step where the tenant interacts with the BGP VPN API. It will associate this port 1, to VPN red, which is our VPN, with a prefix route, which is the 10.8.8 prefix for our Anycast service. And now we can try and hope. OK, so I have interesting error messages on the router side. So interesting. So here, something changed. What we see on the router that we have two routes that have appeared. One which is the route to the port itself, to the IP allocated by Neutron for this port. We won't use it. But we have also the route for this Anycast IP address. It's a good sign. We should be able to resolve Vancouver.demo. It seems to work. Cool. Are you sleeping or? Okay. Because I'm not sure that the rest will work, so it's better if you close now. So now we'll just do a second port, a second VM, same thing. So this time the cloud init file is different. Instead of replying 1.1.1.1, this DNS server will reply 22.22.22.22. But the rest is completely similar. And we can check that the new address, the new route is advertised. Actually, I can actually make it more readable by only displaying the routes for the prefix that is of interest to us. Yeah, so here, our router has seen. Actually, it's not very readable this way. Oops. Our router has seen two routes to 10.8.8.8. And well, we know that it will do multipathing, load balancing, equal cost multipath to reach our destination via two encapsulations, one using label 29, one using MPLS label 22. Interestingly, we didn't capture anything here. I'm wondering why. OK, I don't know. But the traffic is flowing. We had an answer. So let's see what happens now. The DNS resolution still works. We had an answer from the first VM, but it's OK. We have two. We don't know. It's not random. It's hash-based. But we have to test multiple times. Hey, we had an answer from the second one. We can actually make it a bit more interactive by running multiple queries and displaying the result of the DNS queries every second. So every second, it's doing 8 queries to the Vancouver.demo host and displaying the results. So we see that we have a load balancing that's not, let's say, completely even because it's pseudo-random. But we see that load balancing is happening. And we actually see on the bottom right corner that we have actually MPLS traffic. I could actually stop it to describe what we see. So here we have the packet from the end user to the DNS server. So it's a GRE packet containing an MPLS packet with label 19. The packet is the IP packet containing this is sent toward our compute node, and it actually contains an IP packet toward the DNS address with a DNS query to Vancouver.demo. And just right below, we have the answer by the DNS server sent toward the end user with the answer. We can actually create a third server.
So you tell us when to clap next time.
Sorry?
You let us know when we have to clap next time.
Oh, yeah, well, at the end, it should be fine. If it works. I mean, yeah. Well, the only trouble with this demo is that it's a very simple demo. Ideally, you should only start advertising the IP when the DNS server is ready. And it takes some time for the VM to boot, so I'm talking a lot so that I'm sure that it's booted. But ideally, you would have, for instance, a hit template. 5 minutes should be fine, but yeah. You should have a hit template with wait conditions so that the server is creating a trigger in hit after it completely set up the DNS server and started it, so that the address advertisement is done afterwards. So here we have created the third VM, and we have actually the traffic load balance between all the destinations. We can actually do now scale down. We just delete DNS VM1. And pretty quickly, we see that so we have a short interruption here, but right afterwards, we don't have any more served by DNS VM1. And then I can actually remove DNS VM3, and we will end up with only answers from the second VM. That's it. Thank you. OK, so you pretty much, I hope, you pretty much understood the kind of thing that you can do with the BGP VPN API, at least in one use case. There are actually plenty of use cases where you want this kind of interactions with the BGP VPN routing. Let me tell you what's next in the context of this project. So for Rocky, we are finishing features that we planned initially for Queens, in particularly implementing the support for a specific attribute allowing you to control whether or not routes of a Neutron router are advertised in a BGP VPN. On the radar, perhaps for Rocky, but more likely for Stein and after, as possible API evolutions, we have BGP as a service. We are considering adding triggers in the API so that we could control the enabling of a BFD health check between VMs, for VMs to advertise routes to VMs only if they are alive, using the BFD protocol. We are also considering adding a way to control BGP communities. We have discussions that started during the summit to add a new BGP VPN type to do point-to-point, which is also called VPWS via BGP VPN API. And also work that we are considering to allow self-service BGP VPN. So all these are possible API evolutions, nothing we have committed on at this point. Also, two things that could be considered is extending the set of solutions supporting BGP VPN. As I said, there are already quite a lot, but we are interested in seeing drivers for all SDN controllers so that the toolbox is complete. And OVN and Dragonflow are two solutions for which we would be happy to see a solution, drivers being implemented. Something which is related but not directly coupled to BGP VPNs is the Neutron interconnection proposal. You have a link at the end of this presentation if you want to read it. It's a proposal to let cloud users get private on-demand interconnections without the overhead of IPsec. So, as a wrap-up, the Neutron BGP VPN API extension provides key features to let us, telcos, but also people preparing VNS for telcos, do NFV interconnections in flexible ways. There are many use cases as well beyond NFV, such as multi-DC or inter-DC, and also interconnects between the cloud and business VPNs. Of course, this is open source, so your contributions are welcome. And they're actually needed to keep the project alive and kicking. The best way to join the people working on the project is the OpenStack Net BGP VPN channel on IRC. That's it. I will just display on the last slide the reference because this can be useful to have, especially in the video. Are there questions? I think we have maybe like seconds for questions. Yeah. There is some time. Are there questions? Don't be shy. Usually people have questions on BGP VPNs. I was hoping to be clear, but not that much. OK, thank you.